Folks, for those of you who are with Lynn Pham, I got some exams that weren't picked up on Friday and some bonus quizzes. So if you belong to Lynn Pham and you didn't get this stuff, see me after our chat. You can get it. Bonus quiz 2 is posted. How many of you noticed this? Up to 210 points earnable on this thing. Some of you need the points. Go get them. You will see, as I promised you. This bonus quiz intends to reinforce the skills which I saw many of you to be deficient in regarding Exam 2 performance. Material balance, charge balance, writing and calculating equilibrium constants, analyzing the equilibrium system after you have the equilibrium constant evaluated. Which of course means at the minimum we've got to pay attention to stoichiometry. Fundamental considerations regarding thermodynamics. Since all of Exam 2, like all of this bonus quiz, is about equilibrium. And equilibrium is strictly and exclusively a province of chemical thermodynamics. So get at this stuff. You'll notice that if you've not yet seen the bonus quiz, time limit is a week from today. That gives you plenty of time. It's 2 pages this time. Since there are 2 aspects of equilibrium system analysis, each of which immediately parallel question 11 from Exam 2. And the key's posted for Exam 2 as well as for bonus quiz 1. So get at it. And bear in mind that come Exam 3, you're going to see these issues raised again. So I hope, independent of the rules available for your operation in dealing with bonus quizzes, that you make every effort to understand this stuff. That's where it's at. Now then, first, as a pickup from what you folks did Friday regarding this electrochemical cell, the diagram for which is in the notes, I believe, on page 22.8, and there's some errors in the cell diagram, which if you were with us on Friday, you heard about. The zinc electrode is mistakenly labeled as cathode in the notes, I believe. It's supposed to be anode, because each electrochemical cell consists of 2 electrodes. One called the anode. What happens at the anode? Oxidation. And the other called the cathode. And standard practice in writing a cell diagram is to show the anode and its components on the left, the cathode compartment and its components on the right. And for the cathode, there are various materials which can be used for the cathode material itself. It is the electrode on which reduction occurs. In this case, since we're going to reduce copper ion, we're going to use a copper strip as the cathode and just enlarge the size of the copper cathode material. I could use a silver electrode here if I wanted to plate copper on silver. The only requirement being in constructing the cathode half cell is I cannot use a cathode material if I want this cell to operate properly. I can't use a cathode material which will do what? Sodium's a metal. Sodium's a good conductor. Can I put a strip of sodium in here? The answer is sure I can. I can put anything in here. But if I put a strip of sodium in here, will this system run appropriately? No, why not? Why not? What'll happen? React with water. It'll murder water. It'll murder this stuff. It'll murder this stuff. It'll murder every component of this system. So you cannot use a cathode material which is capable of reducing the contents of the cathode half cell, because it is in this half cell where reduction occurs, which means the oxidizer is in this half cell. And in this case, the oxidizer is hydrated copper ion. Now, back to first principles. Let's imagine you are assigned the task. This is what you started to talk about on Friday. You're assigned the task of using copper and zinc. That's it. Copper, zinc. And zinc sulfate solution, copper sulfate solution. We got, for our example, 1 molar, since these correspond to standard state concentrations. Okay? That's it. From these 4 chemical materials, copper strip, zinc strip, a solution of copper sulfate, a solution of zinc sulfate, how can you construct an electrochemical cell which will function so as to deliver usable electrical energy? Well, you got to find out 2 things if you don't know before you start to assemble a cell. Which metal is the stronger reducer? And as soon as you find out which metal is the stronger reducer, you will immediately find out that the hydrated metal ion of the stronger reducer, is the weaker oxidizer or the stronger oxidizer of the 2 hydrated metal ions. The one derived from the copper, the one derived from the zinc. If we find zinc to be a stronger reducer than copper, what does that tell us about the relative oxidizing strengths of hydrated zinc ion, the conjugate oxidizer of zinc, and hydrated copper ion, the conjugate oxidizer of copper, at least in water solution? If I find that zinc is a stronger reducer than copper, what does that immediately tell me about the oxidizing power of hydrated zinc ion compared to hydrated copper ion? Weaker. Which one is weaker? The hydrated metal ion of zinc. Just like the acid-base stuff in terms of the way you read it. Remember what we found out? If acid HX is a stronger acid than acid HY, with the acids in our acid column increasing in strength from bottom to top, that means that Y minus is a stronger base than X minus. Well then, if I find that zinc is a stronger reducer than copper, that means this is a stronger oxidizer than this. It's just like that. Same idea. That's the way this extensive table of half reactions that you see in chapter 22, table number 2, was that 43 or 44 or 45 half reactions in there, something like that? Hey, that's the way that table is to be read. When you look at this table of half reactions, the one that's in the notes, look at it now. Because if you can't read that table, you're not going to do anything successfully with electrochemistry. It's like, hey, we spent a lot of time seeing to it or trying to see to it in chapter 18. You could read an acid-base table. Well, now you got to read this table. When you're looking at this table, can you tell me what's the strongest reducer listed in this table, the one that's in the notes? What is it? Lithium metal. So immediately you now know that regarding the information in this table, which is a package of thermodynamic information, just like the acid-base table, what's the weakest oxidizer in this table? It's hydrated lithium ion. What's the weakest reducer? listed in this table. Fluoride ion, aqueous, because it is derived from the strongest oxidizer listed in this table, elemental fluorine. Remember fantastic fluorine got the highest electronegativity? Hey! Fluorine is an absolutely potent oxidizer. It's an electron hog. Does that not correspond to its highest electronegativity value? I mean, electronegativity does not measure electron affinity directly, but it is a measure of electron affinity. Electron affinity is an energy. Electronegativity is a measure of the ability of an atom in the covalently bound state to attract valence electron density to itself, and in so doing stabilize the valence electron density. We've talked about this before. I just want you to see how the stuff we're presently talking about relates very much to stuff we've already talked about. Now back to Chemistry 2045 laboratory. You got a strip of zinc, a strip of copper, a copper ion, and zinc ion. You want to know which is the stronger reducer, zinc or copper. So you do a simple experiment. You remember what you did in 45 lab? You put the zinc strip in copper ion solution and the copper strip in zinc ion solution. That's all you got to do. Because in only one of these will a redox reaction occur. Now I could stand here and put the copper strip in zinc ion solution, but I don't want to soil my copper strip. No reaction will occur. But here's a little bit of copper ion solution. 1 molar. And here's a zinc strip. Small zinc strip. Watch what happens as soon as I touch the zinc strip to the copper ion. See the bottom here? That's where we're going to make the contact. That's where I will make the contact. Look at all this blackness. The blackness is copper. You say, gee, that doesn't look like copper. I agree. But this copper forms so rapidly that you have not yet been able to develop the lattice which shows this characteristic bronzish color. If I leave this in here for any length of time, you'll see the bronzish color begin to develop. We'll put it in there for a while we carry on with the investigation that we want to do in regard to construction and assembly of an electrochemical cell which functions to give you usable electrical energy. Because when we have the zinc strip in direct contact with copper ion, are electrons flowing? Is a current flowing? Absolutely. But it's flowing directly from the zinc atoms in the zinc strip to the copper ions in solution. That's a short circuit. This does not give me usable electrical energy. Because I got to make those electrons, as they flow from the zinc atoms to the copper ions, I got to make these electrons flow through an external circuit into which I can fix a socket or something like that and plug in my toaster or whatever. So I can use this electricity. I can't do anything with it now. Didn't have this in here very long. You already see the copper color developing? It doesn't take long. Okay? So what you have to do to run an electrochemical cell, which by definition means a cell which will give you usable electrical energy, is to physically separate oxidation from reduction. That's what you have to do. This is the way it's done in your automobile battery. This is the way it's done in flashlight batteries. This is the way it's done in any battery system. Now you can find this out by taking your automobile battery out of your car and sawing it in half. But then you might have to buy a new battery. So it's easier to look it up on the web or in a textbook which has illustrations of such, and it'll show you how it works. Same thing for a D-cell battery, a C-cell battery, or a dry cell, or any battery. They all work the same way. Okay? So here's what I've done. I have, instead of one beaker, 2 beakers. One beaker containing zinc sulfate solution in which I have immersed the zinc strip. And a second beaker in which I've got a copper strip immersed in copper ion solution. Question. Any electrons flowing in this system? Any electrons flowing in this system? In this system, are electrons from zinc atoms flowing to zinc ions? While simultaneously as zinc converts to zinc ions are reconverting to zinc in this system. Yeah, electrons are flowing. We'll talk further about that when we get to specific cells, electrochemical cells known as concentration cells. Not now. But that leads to no net change in the system. So practically speaking, there's no current flow. So, let's get these two half cells, the copper ion half cell, the zinc ion half cell, connected. All right? I got a gizmo here, which can function as, among other things, as a voltmeter. Sometimes I connect the polarity in reverse and it'll try to give me a negative reading. I'll have to change the polarity, but I think I got it right. For some reason I can't get a reading. Why can't I get a reading?
Salt bridge.
I don't have the systems connected. I've provided a path by which electrons can travel from zinc, since zinc is a stronger reducer than copper, through the wire, through the meter, and into this system. But how can they get back? I have an open circuit. So here's where the salt bridge comes into play. This thing, pictorially represented here. I made off with one salt bridge. This, I believe, it's either a saturated, whoever made these did a stupid thing. Didn't label them. All I know is that this is a salt bridge. But I don't know what's in the salt bridge. Most of the time, these simple demonstration model salt bridges are made from saturated sodium sulfate or saturated potassium chloride. Because the component ions, sulfate ion, potassium ion, sodium ion, chloride ion, often don't react with either of the components of the half cells. We don't want that. All we want the salt bridge to do is to complete the circuit. And if I have a paste of an ionic compound, a liquid paste of the ionic compound, hey, I got a medium in which ions can flow. Ions are charged particles. That's a current that completes the circuit. So let's see here. Whoever made this thing also didn't make the arms the same length. So we have an interesting system here. Let's see. Let's try this. I guess that's in there. Yeah, that's in there. Okay. And now let's see what we can get here. Now, I want you to look at the half reactions in the table. The table that's in the notes. Look at the half reactions we're considering. You did this on Friday, do it again. You're looking at this. What I'm doing in writing these half reactions is also to illustrate the coupling process, which you learned about on Friday. Because in making an electrochemical cell, and using the half reactions in our table, we could use the half reactions in any table. You pick any two half reactions, I don't care which ones. Pick any two. If you pick one that needs an electrode material, you'll have to supply it with electrode material, like the standard hydrogen electrode. Gas phase hydrogen molecules are not particularly good current carriers. Take the half reaction from the two you've selected. Take the half reaction which has the higher E0 value and write it as it is. So, if you find the half reactions that we here have written, you'll see that zinc becoming zinc ion has a higher electrochemical potential than copper becoming copper ion. You see that? What is the electrochemical potential for this? Tell me what it is. You're looking at it. Now then, for copper becoming copper ion, look at the table. The electrochemical potential is minus 0.34 volts, isn't it? And these are all measured relative to the standard hydrogen electrode, our thermodynamic standard for measurement of, in this case, E0 values. Well then, since this is the half reaction of lower electrochemical potential, in the coupling process, I have to take this half reaction, write it in the opposite direction. I've already done that. And when I write it in the opposite direction, I have to change the sign on the electrochemical potential. So this becomes plus 0.34 volts. And how then do I get the electrochemical potential, the standard electrochemical potential for the electrochemical system? Add them up. Big deal. So the two sig figs, when I add these up, I get plus 1.1 volts. Here's our gee whiz student demonstration. Here's what we got. Can you all see it? Or at least those of you who are up close, can you see it? What are we reading? 1.09, not bad. Okay? Why is it not exactly 1.1? I don't know. Are these solutions exactly 1 molar? I don't know. Is there a degree of resistance in this salt bridge for which I cannot account? I don't know. But that's not bad. 1.09 volts instead of 1.1 volts. And now, as we said, we've got a complete circuit, and we have physical separation of oxidation from reduction, which is required in order to circumvent the possibility of short circuit. You've got a short circuit, you've got current flowing, but it's not usable current. Okay? So I'll for now disassemble this. Turn this off. And carry on with the other investigations that we would like to get at. Let me tidy up my poor man's salt bridge. The poor person's salt bridge. By the way, regarding poor person rather than poor man, I am a firm believer that one thing that people have got to do in this world, if we're going to in fact have a chance to achieve peace, is to see to it that in every culture, women have just as much power and say-so as men. Period. End of story. And until that happens, it ain't going to happen. So you gals, hey, flex your muscles. Don't be shy. Don't be bashful. Do what you can to help women in other cultures have positions at least of equal say-so with men. And don't stop short. It's got to be that. Then we got a chance to have peace in this world. All right? That's the political comment for today, unless I think of something else that might be worth saying. And we go on. We're now going to do some simple demonstrations. And we're going to develop a half reaction table. Not nearly as extensive as the table you see in the notes. We're going to do a few simple investigations, some of which, in fact, you already were asked to consider in Chemistry 2045 laboratory last term. Because I wanted the work you did in 45 laboratory to lay foundation for this. Because this is supposed to be an expansion, an extension of what you learned in 45 lab. And redox reactions, which is what electrochemistry studies, are arguably the most important reactions there are, category-wise. Why? Because more reactions are redox than any other type. And redox reactions are the reactions which we commonly use to give us usable energy, like electrochemical cells. Hey, pretty important, don't you think? All the reactions that take place in our system when we munch food to give us energy. Redox. Important, don't you think? So here's the experiments we're going to do. Notice that a number of these investigations I've tattooed with a circled asterisk. Because we won't, in fact, actually do those investigations, because they lead to no reaction. So if I assemble a no reaction system and put it on a desktop, or have you do this in laboratory, and tell you to stare at it, you're going to get bored fast. So we'll simply try to expedite matters regarding no reaction systems by telling you that some of these systems are no reaction. But in our conversation, we'll remind you what the significance is of a no reaction system compared to a reaction system. Okay? We've already done that today. Zinc in copper ion reaction. Copper in zinc ion, nothing. Consequence, zinc a stronger reducer than copper, and hydrated copper ion a stronger oxidizer than zinc. Hey, that's the theme of all this stuff. So, here we go. The first one is the most fun. And as you might well expect, the most risky. That's why it's the most fun. See these notes? See the burn holes? When I did this in a previous class, the piece of sodium I used for the investigation we're now going to look at was so big that some of it jumped out on the beaker and landed on my notes and burned holes through it. Oh, I cried. I don't want no holes burning my notes. I don't care if they burn holes in me, that's okay. But don't touch my notes. Okay. Perhaps you will recall that you've already seen this demonstration. Let's get this stuff out of the way. All right. I'm going to collect some deionized water. In this large tall boy beaker. I'm going to treat this deionized water with some phenolphthalein. You know how phenolphthalein behaves. If the system is fairly basic, you'll see a red-pink color, but colorless otherwise. No color. Phenolphthalein kicks color-wise at about pH 9.2. Well, this is deionized water. It runs at a pH about 6.5 commonly. And now we have here an extremely elegant sensitive conductivity detection device. For a couple $1,000, you can have one of these. Get off of there. To show you that our conductivity device will function, we're going to provide a power source and then screwdriver using the business end to bridge the leads. Aha! So this shows us that when I bridge the leads, the electrodes connected to the light bulb in the socket, current flows and the light bulb glows brightly. Okay? Now I don't want to bridge the leads with me. I don't want to see if my nose will glow like Rudolph. Fabrication of this device leaves something to be desired. But I will add some more deionized water so I can be sure that contact is established by the contents of the beaker with the electrodes of our gadget. All right, we're okay now. No glow. Now we shouldn't be surprised at the no glow feature because, as we know, the ion concentration, total ion concentration for our deionized water is only what? What is it? Total ion concentration. What is it? 2 times 10 to the minus 7, right? 1 molar hydronium, 1.0 times 10 to the minus 7 molar hydronium ion and 1.0 times 10 to the minus 7 molar hydroxide ion. All right, that's a pretty small ion concentration. Upshot, in order to measure the conductivity of deionized water, you have to have a very sensitive conductivity gadget. Our light bulb device is far too crude to meet that requirement. So for now, I'm going to unplug the power, in case I make a mistake of bridging the leads, the electrodes with myself, and this is my lid for my salt bridge. I want to keep this stuff. Hope I don't run out of beakers. Clean this up. Our shield. And in here I have some natrium. You know what natrium is, don't you? Na. How in the hell could you call Na sodium? How can you call Ag silver? Well, these come from the old Latin names. Natrium, which became sodium, and argentum, which became silver, and stuff like that. I have sodium, some chunks previously cut, stored underneath a liquid, so air contact is not established, because sodium reacts immediately with oxygen and air to become sodium oxide or sodium peroxide. Smells like kerosene. What do you know about kerosene? Flammable. It's flammable. Is kerosene flammable because it is an oxidizer or a reducer? The simplest hydrocarbon, also used commonly as a fuel source, is methane. You're familiar with methane? You may at home have a gas-fed burner using propane. Maybe you've got one of these little flick-the-bic devices which uses butane. These are all common fuels. Are these fuels reducers or oxidizers? Kerosene is also a hydrocarbon. This sodium is underneath a layer of kerosene. What do you know about sodium? Strong reducer, strong oxidizer? What do you think? Strong reducer. Didn't you find in our table that lithium is the strongest reducer listed? Right? Are lithium and sodium in the same chemical family? Right? So do you expect sodium also to be a strong reducer just because it's in the same chemical family as lithium? You think that's a fair bet? You betcha. And this sodium is not reacting standing in contact with kerosene. Is kerosene a reducer or an oxidizer? Reducer. You reducer. You put sodium in contact with anything that's got any reasonable oxidizing strength and you got troubles. How about water? Water a strong oxidizer? If, for example, we put zinc in water, or copper in water, get any reaction? You ever see fountains where people throw pennies in fountains? You know, pennies today are principally zinc rather than copper, because zinc's a lot cheaper than copper. You see any reaction happening when people do this? No. So water is not a particularly good oxidizer. Can water oxidize sodium? Well, for those of you who did assignment 5, part 1 in 45 lab, and also had the pleasure and privilege of watching the very famous actor do the demonstration of the sodium-water reaction, which will now be repeated for your educational pleasure, you know the answer. Now, what am I going to do is to get my tweezers, dry paper towel, catch some sodium with my tweezers. Well, that's a pretty good sizable chunk. Okay. I don't want the kerosene being part of this investigation. Dab off the sodium. With paper towel. Where'd you go? There you are. Okay? It's not a particularly large chunk of sodium because I don't want a particularly vigorous outcome for this investigation. Now, wait. You folks up close, be careful. Move this away. Uh-oh. Catch. Drop and run away. Fire. Let there be fire. We'll talk about the fire in a moment. Do you see that the phenolphthalein is indicating the presence of a system becoming basic? Now, I purposely rigged up this demonstration apparatus by wrapping strong tape around the beaker so that if an explosion takes place, the beaker shouldn't shatter. And that's a nice, sturdy, rather heavy plexiglass lid, this thing. You saw I burned my notes, and I burn me, I don't care, but don't burn my notes. I can't stand that. All right? All right, now then, what did we see? We saw the sodium skittering about the surface of the water because sodium is less dense than water. If you look closely, at least those of you who are up close, did you see the sodium assume a spherical shape? Because sodium has a low melting point. And the heat of this reaction is quite exothermic reaction. The heat of this reaction is enough to melt the sodium. So you wind up with a lump of liquid sodium skittering about until all the sodium disappears. So regarding A, sodium and water. A reacts vigorously with water, giving basic solution. Phenolphthalein became a distinct red-pink as a gas is liberated. The gas which was liberated accounted for the flame you saw. Remember seeing the flame? Okay. Now let's do one more investigation with this system. Let's go back to our conductivity gadget, which you recall was not capable of detecting the very mild conductivity of the ionized water. We got the leads in there. And how about that? Now we get a pretty bright bulb glow. What's that mean? Basic solution as gas is liberated, and you fill in the blank, are produced. What goes in the blank? Ions, you betcha. Because now we got a solution whose ion concentration is sufficiently great to support current flow. Now, just for safety's sake, I'll unplug and we'll go back to the board. And based on this information, let's see what we can do to come up with some half reactions. We start by recognizing that sodium is a potent reducer because of its periodic position and because, as is now illustrated, demonstrated ability to reduce water, water not being a particularly strong oxidizer. So, we'll now take advantage of something I hope you learned in 2045. These 1A atoms. In what way are these 1A atoms similar? Did you learn in 2045 that the most important periodic property by far is... What's the most important periodic property? I'm listening.
Charge density?
These are atoms. They don't have a charge density.
Well, positive charge density.
They're atoms. They don't have charge densities. Wait a minute. We're talking about atoms. What is that? Nope.
Stability?
Stability? Nope.
Size?
Nope.
Configuration?
You're getting there. I heard electron configuration. Specifically, what electron configuration?
After the...
When an atom reacts, are all the electrons involved?
No.
Which electrons are involved?
Valence.
Bingo. That's the most important periodic property. Valence electron configuration. That accounts for why the atoms are grouped as they are grouped. Because of valence electron configuration. All these 1A atoms have have a single s valence electron. That's it. So their most common reaction tendency, in fact, the only reaction tendency they ever show is to do what? What's the only chemistry these 1A atoms ever show? Discounting hydrogen. I'm talking about the metal atoms in family 1A. What's the only chemistry they ever show? Lose their single valence electron and become cation with a charge of +1, because in becoming a cation with a charge of +1, what kind of configuration have these atoms developed? Yeah, that's it. By losing 1 electron per atom, these atoms have become exceptionally stable, haven't they? Because they developed valence electron configurations isoelectronic with that of their nearest neighbor noble gas. How about that? So, we're making Na plus AQ because it happened in an aqueous environment, and an electron. And now you can recognize why. If students in my 2045 class tell me that this symbol and this symbol mean the same thing, we have a problem. They're required to demonstrate the sodium tongue test. Did I not tell you about the sodium tongue test? Every student who tells me that this symbol and this symbol means the same thing must come to the front of the class. And then they are required to stick out their tongue. And I take a nice scoop of sodium chloride, because that's very rich in sodium ions, and I scoop it under the tongue and I say, reel in your tongue. And I say, now describe your reaction. And if they're very careful, they can say, well, it's a little bit cooling, because sodium chloride dissolves endothermically in water. A little bit cooling, and they get, of course, a salty taste. But that's about it. Nothing much of consequence happened. So I say, okay, stick back out the tongue. And I rinse it off with deionized water, and then I get a nice chunk of sodium. Put it on the tongue. Reel it in. Tell me what happened. Pow! No more tongue, no more teeth, no more student, and no more anybody telling me that these symbols mean the same damn thing. Because they do not. This thing is very reactive and has a very high energy content. This thing is very peaceful. Admittedly, it has a charge, but from a chemical reaction standpoint, this thing is about as peaceful as can be. So, we now in our table have a half reaction we can write. In the investigation we just performed, sodium metal, the reducer, lost 1 electron per atom and became sodium ion, the conjugate oxidizer of sodium metal. At least the conjugate oxidizer of sodium metal in aqueous medium. What's the next half reaction? Well, sodium reacted with water. That's all we started with. So the next half reaction has got to involve water. And it's got to involve water in what capacity? Water behaving as a reducer or water behaving as an oxidizer? What? Sodium behaved as a reducer because sodium got oxidized, didn't it? So in what capacity must water behave? Got to be an oxidizer, because in this system, is water going to get oxidized or reduced? Sodium, the reducer, got oxidized to sodium ion. So water, the oxidizer, is going to get reduced. So this has got to collect electrons. Now let's make some decisions as to what water becomes when it collects electrons. We saw a system becoming basic. And we know we started with strictly neutral materials. And we know by the principle of electroneutrality that if we ran a reaction in which positive ions were being formed, since the original system had no ions, practically, that beside making positive ions, we have to make negative ions. And negative ions derive from water, which can account for the system becoming basic. You know what this negative ion is. What do you think it is? Hydroxide ion. How about that? And the gas was produced. In fact, the gas burst into flame in this system. So we're going back to water because we know sodium ion is not a gas and hydroxide ion is not a gas. So we're asking the question, from water, based on its elemental composition, what gases can be derived? H2? O2? Or both? Question. When water behaves as an oxidizer, as it did in this system, is the gas derived from water? Or is the gas derived from water? Strictly hydrogen, strictly oxygen, or possibly both? 3 choices. How many vote that the gas derived from water, when water behaves as an oxidizer and in so doing gets reduced, the gas derived from water has got to be hydrogen and nothing else? Oxygen, nothing else. Possibly both. Well, the best way to do this is to catch some of the gas and do some chemical analysis of it. But we can find out what the gas is by simple oxidation number analysis. Hey, we've done this before, haven't we? Water. Electron parceling. Oxidation state for the oxygen atom components of water, -2. +1 for each hydrogen. I put quotes because these are not charges, they're oxidation states. Gas, hydrogen, element. Oxidation numbers are? Oxidation numbers are? 0. Can I go from -2 oxygen by collecting electrons which are minus and become a 0 oxidation state oxygen? Hell no. How can I go from -2 to 0 by getting things that are minus? I'd have to become more minus. But can I go from +1 hydrogen to 0 hydrogen by collecting electrons? Absolutely. So with this simple device, oxidation number analysis, we have recognized that the gas produced by this reaction is strictly hydrogen. Is hydrogen a fuel? Is hydrogen a fuel?
Yes.
Absolutely. And it's a wonderful fuel. Because if hydrogen as a fuel reacts with oxygen as an oxidizer, what's the only product we get? Water. Any pollution? None. I've argued for years in my chemistry class that the chemical engineers and other people who investigate such stuff had better get going on figuring out the simple and best way to harness solar radiation, because that's the only large free energy source we have, to electrolyze water and make hydrogen and oxygen, particularly hydrogen. Because when hydrogen is used as a fuel, the only reaction product is water, and there is no pollution. And this is a very high energy liberation process. Wonderful. Now, do you think the people who make automobiles are for this? You think the gasoline companies are for this? Well, I don't give a damn. Because if the people of the world want to continue for a good long time and be as happy and healthy as they can be, they better be concerned with this kind of stuff. So this kind of stuff, amongst other things, are in your laps, folks, because you're the next generation. And I want to do the best I can to make you, the members of the next generation, as successful as you can be. How about that? That's one of the things this gathering is about. So here's what we have. Is this an equation? No. Doesn't balance. Well, what can we do to turn this into a balanced statement? Well, for starters, if we don't do anything but simple arithmetic, on the right we've represented 3 hydrogen atoms from a fundamental particle standpoint, so at the minimum we got to have at least 2 of these. And if I have 2 of these, and put a 2 multiplier there, have I got material balance? I have material balance. Do I have an equation? What can I do to make an equation? Done. And now, if I wish to add this half reaction to the table we're developing, if I want to put this half reaction in there systematically, I got to take it as it is and turn it around, write it in the opposite direction. So that's half reaction number 2. And do you believe it's fair to say, with no qualms about it whatsoever, that the work we've done corroborates that half reaction 1 as a reducing half reaction, because it corresponds to oxidation. Half reaction number 1 is more favorable than half reaction number 2. This is a stronger reducing system than number 2. Is that fair? Do you think I could continue to shovel sodium in this beaker? Yes. And if I continue to shovel sodium in this beaker, do you think it would ever come to equilibrium where some unreacted sodium would remain in contact with water? Never. So it tells me half reaction number 1 has a much higher electrochemical potential than half reaction number 2 as written. All right? Now let's look to see what else we have over here. Zinc in water. Nothing. If I put zinc in water and nothing happens, what does that tell me about this half reaction? Zinc in water does nothing. Sodium in water reacts vigorously. What does that tell me about this as a reducer strength-wise compared to this? Which is the stronger reducer, sodium or zinc? Hey, sodium reduces water readily. Zinc does nothing. So I know zinc is a weaker reducer than water. That means this half reaction has got to be underneath the sodium half reaction in the table. And if zinc does nothing with water, then it's got to be underneath number 2. You see how this table is beginning to develop? From a meaning standpoint, just like the acid-base table, this reducer can reduce this oxidizer, which means the conjugate reducer of this oxidizer has got to be a weaker reducer than this reducer. Just like acids and bases. The language is a little bit more clumsy because you got to use more words, but you read it the same doggone way. Can this oxidizer be reduced by this reducer? Hydrogen plus hydroxide ion. That's a reducer system. Can it reduce this oxidizer? If I take sodium chloride solution, which has got sodium ion in it, and I bubble hydrogen through the solution after I've added a bunch of hydroxide ion, am I going to turn this into this? Not ever. No way. This is a stronger reducer than this, which means that this is a stronger oxidizer than this. Now we added this system to the table. Hydrogen plus hydroxide ion. Can that reducer reduce hydrated zinc ion? Can zinc plus water, can zinc reduce water? Hey, no, we put the zinc in water, nothing happens. See how this reads? The reducers are getting stronger from bottom to top, while the conjugate oxidizers of these reducers are getting stronger from top to bottom, just like the acid-base table. Now let's try another investigation. Oh, my. Okay, here's a beaker. Chalk stain now. We have said Zinc, water, nothing. So I'm not going to bore you with this zero result investigation. Here's my zinc strip. And now I'm going to treat the zinc strip with some 1 molar sulfuric acid solution. That's investigation number 3. Now, while we're waiting for something to happen, if we're going to get at the chemistry shown by this investigation, if we're going to get at the chemistry shown by this investigation, what do we have to do? Right now. What do we have to do for that system? PSI! Come on, do it right now. There's no escaping from PSI. Never. Anything going on in here? What? Describe it loudly and clearly. They all need to know.
I guess it's oxidizing the zinc.
I can't hear you. I can't hear you. Your turn. See something going on in here? What's going on? Your turn.
Yeah.
What's going on in here?
Well, I see some possibly bubbles.
Possibly bubbles.
Yeah.
I never saw possibly bubbles. Are we seeing bubbles or not bubbles?
They don't seem like bubbles.
They don't seem like bubbles. What do they seem like?
Little small particles.
Little small particles.
Yeah. Whitish in color.
Yeah.
Yeah, what?
They don't look like bubbles. I mean, the zinc is reacting with the H2SO4.
How do you know?
It wasn't doing that, and then the zinc was in there.
What's the it that it wasn't doing? I want to know what you see. It causes laughter.
Apparently.
Tell us what you see. Look specifically at the surface of the zinc strip.
It looks like it's being deteriorated.
Your turn. What do you see?
I think it's turning black.
Black.
Did you take it out?
I don't see any black there.
Oh no.
What's happening on the surface of the zinc strip?
Some bubbles or
Bubbles! All right, we got bubbles. Back to bubbles. Your turn.
I agree
You agree with what?
that there is bubbles.
You agree there's bubbles. Does bubbling look vigorous? Not vigorous. My golly, look at all this cloudy thing taking place up here. Not vigorous?
Well, I mean,
Yes or no?
okay, yes.
Okay. Yes. Boy, I cowed her into that one. What do you see?
Maybe a precipitate forming.
Precipitate. I don't see any solids on the bottom of this.
I mean, it looks like murky water, so
Murky water.
like cloudy water.
Cloudy water. Okay, it's going to rain. What do you see?
Is the zinc being stripped off the metal?
Are you asking me or telling me?
Looks like the reaction stopped.
Stopping? Well, I mean, I'm seeing frothy and bubbling going on in there all over the place. That's what I'm seeing. What do you see?
It's bubbling.
It's bubbling. What's it?
the zinc,
The zinc is bubbling.
and it's like giving off.
Giving off. We don't know what is giving off. Describe.
It's cloudy.
It. I don't want to hear
The
it.
solution is cloudy, and there seem to be little like white particles floating around.
White particles floating around. Have you ever aerated a sample of water?
Not that I know of.
You know, bubbling a good stream of air through water? Not done it? These white particles floating around. You still see white particles floating around?
Yeah.
You do? Where are they?
The solution, I mean, it might be on the wall of the glass.
Now it's on the walls. Well, if it's on the walls, they're not floating around.
Okay.
Okay. I want you to tell me what you see. You keep letting me talk you into things. Now then, what is going on? Vigorous reaction. Gas liberated. Zn is disappearing. Now, take note that in order for us to recognize that zinc in this transformation is in fact disappearing, we'd have to leave this go on for a fair amount of time so we could observably detect that we now have reduced the size of the zinc strip. Now, I don't want to leave this go on for that long because then I got to go get some more zinc strips. That might take an extra effort on my part. Can't do that. Okay? Zinc in this system is being oxidized to this thing. Did you learn in paying attention to the rules for writing half reactions that if a metal is oxidized in water, that's what's going on here. Pardon me, water solution. If a metal is being oxidized in water solution, unless you are told otherwise, what will the metal convert to? If a metal is being oxidized in water solution, unless you are told otherwise, what will the metal convert to? A hydrated metal ion, probably hexahydrate. That keeps what we have here. Now let's look at the PSI for sulfuric acid solution. What is oxidizing zinc? What's causing this reaction to take place? Is it this? Zinc does nothing in water, right? So this isn't the oxidizer. So you got a choice between these two. Now to decide on the choice between these two, let's see if we can decide what this gas is. Any bets? Let's imagine we simply collected a sample of the gas, analyzed, we find it's hydrogen. So whatever is being reduced, whatever is doing the oxidation of zinc, is giving as a reduction product hydrogen. So I ask a question. Which of these do you think is being reduced and why? Look at what we did with water. When water got reduced to hydrogen and hydroxide ion, it was the +1 hydrogen atoms in water that collected the electrons to become hydrogen atom zero oxidation state, which then bound with each other to make hydrogen molecules. From which of these can I more readily obtain +1 oxidation state hydrogens? Because I got to give those electrons to make hydrogen atoms and let the hydrogen atoms come together to make this stuff. From which of these can I more readily obtain +1 oxidation state hydrogens? Which one? Why?
Because it's a better reducer?
This is not reducing.
The oxidizer.
Which of these is the better source of +1 oxidation state hydrogen? And why? Chapter 18. Come on. Why? It's a stronger acid. Statement. When you read the rules for deriving these half reactions, if you haven't read them, you better read them thoroughly before tomorrow's gathering. You will realize that just about every one of these rules depends in some fashion on Bronsted-Lowry acid-base chemistry. How about that?
If something's a good reducer, doesn't that mean it's a greater acid?
No. Acids are normally good oxidizers, not reducers.
But isn't that true?
Well, you say, isn't that true? I don't know what that is.
The more acidic something is, the better of a reducer.
No.
I mean, an oxidizer.
Yes.